Oh, it's too loud. Okay. Do you guys hear that too when it starts recording, so that you're aware of this fact or not?
Yeah.
Okay, very good. So for some reason, Gino did not come back. I don't know, probably he's got also the old link or something like that. Anyway, good morning, everybody who's here. And we're, let me check quickly the email because I think Aaron is trying to connect. And for some reason, and John also asked for the password. And Jackson is having an issue with the internet. Outside of this thing in here. Let me see if somebody sent his request in here. No. And nothing in the inbox in here either. Okay. So we're going to basically do with what we do again. The reason why we're doing this right now is because to prevent any unwanted basically visitors. So we want to make sure that only the students who are enrolled in the class can come in. And if somebody else outside of the class wants to join in, we have to make sure that he or she is thoroughly basically vetted to make sure that they're okay. So we're dealing with chapter 27. Any questions about chapter 27? Because technically we finished chapter 27 for you guys, okay? For those who are going to watch this video later on, please also ask and follow up with any questions on the discussion board on Canvas or on, don't do it on YouTube. I don't think that it's a good idea to ask questions, especially specific to our class on YouTube, but ask it on Canvas, okay? So we're, is there any question about the problem sets that I gave you guys? The ones that you're working on in terms of the homework?
I haven't had a chance to look at it yet. I've been swamped.
No, you guys need to get started on it because it's important in terms of that. We really don't want this to be delayed. And I know we would discuss some of these problems here together. I mean, we did some of them full solutions, some of them were just a partial discussion. So I want you guys to make sure that you started on this thing. Okay, somebody else joined in. Sophia is here. That's good. And we still have Aaron probably still struggling with the connection. Okay. Yeah, I think Aaron is having difficulty with the connection, although I sent him the link. Anyway, basically we're going to finish chapter 27 and start chapter 28, and chapter 28 actually is on Canvas already, the discussion board. So I want you guys to make sure that you're aware of that and that at least you started reading the chapter. Chapter 28 is a little bit easier conceptually. The math in it is a little bit more involved though. I mean, you probably are going to be dealing with cross products in here more than anything else in your lives. And also, it involves also a lot of integrals and things like that. But actually, it involves one big integral, and after that, everything else is easy after that. So it's not really that big of a deal. So let's go back into my notes in here so that we know where we are. And we go in here and start sharing this session with you guys. Oh man, I kind of feel bad because Gino was here with us, and when after I told him to leave now and restart this session, he's not here again, and that's really probably giving also the same difficulty, but we're using the old link too. Anyway, let me share the session in here. So this is the stuff we'll be covering in chapter 28. In part, chapter 28 will be started in here, will be finished in YouTube. The discussion will be completed by Tuesday of next week. And Gino is back. Very good. Okay. So the discussion will continue on Tuesday, and we'll finish it on Tuesday. At this point, I don't know honestly if the lab is going to be also held on Tuesday of next week or not, because we still are missing an essential part of it, and that we did not reach yet. So most likely the lab will be postponed. I know one of you guys asked about the lab, and we still are kind of a little bit behind in terms of content, trying to reach that lab and be able to do it too. We have to get into inductance in order to really do that lab properly, okay? So this chapter deals with a fundamental question, really, and that question has to be answered somehow. And namely, the question is, what is the source of B? Where is that coming from? Okay. We understood from chapter 26, no, the early on chapters that we did together, that charges create electric fields. So as much as a charge creates an electric field, a moving charge actually creates a magnetic field. So the point being is the following. If you have a charge in motion, so it's a Q, and V, that creates basically a magnetic field. This is what observation taught us. And the biggest question that we hopefully will try to answer toward the end of the chapter is, okay, we're going to go through this chapter, see that moving charges create magnetic fields. And what are moving charges, if you guys remember from chapter 26? When a charge moves, what does it do for us? What does it create? On circuits, to be specific. You can answer in the chat or audio. I want to know from chapter 26. So if I have a stream of charges going around, what is that called? Any idea? Anybody? Chapter 26. Are you guys looking at the chat and electric? Okay, an EMF actually is the one that forces the charges to move. So electromotive force moves charges, okay? And when the charges are moving, what is that thing called? Okay, very good. Thank you. That's the word I was trying to get to. Moving charges actually create a current. This is actually what the current is. So basically, if you have a rate at which charges are moving in a circuit, that is what current is. But in this situation, in this picture that you guys are looking at, in here, I have a single charge. I don't have a bunch of them. So if I have a single charge and it's moving, it creates basically a magnetic field. So the magnetic field, and that's why I drew this picture in here for us to see, and that is really the Dark-Hand rule. So without it, we cannot do anything. Okay. So at the end of the day, since charges are moving, it will boil down to the following question in terms of what causes magnetism. It's current. Okay. So that's the answer to it in a nutshell. Which brings me to the last part of this chapter, which we need to somehow explain, and that is bar magnets. And a bar magnet, an electromagnet, yes, we're probably going to understand that using current. An electromagnet is electricity running through a wire, and that wire basically will create magnetism. And you can do an experiment with it by increasing the strength of the current in the circuit and noticing basically the strength of the magnetic field increase with it. Kill the current and the magnetism is gone. So that's an electromagnet. But that's not a permanent magnet. That's a magnet that basically you create it while the current is in the loop. If the current dies, there is no magnet. The question that we need somehow to answer is, what is a permanent magnet then? How is that working? Because I just said that currents create magnetism. So does this mean that in a bar magnet there is a current? Anybody? I need actually everybody to tell me yes or no. You can do it in the chat or you can do it directly. You think in a bar magnet there is, Sophia thinks yes. Even in a bar magnet there is a current. Okay? Anybody else? I need everybody to tell me yes or no. Okay. John Ashton, Okay, at least some people are thinking maybe how can it be current? And they're absolutely right. I like honesty, honestly. Okay, you have a bar magnet. Where do you see a current coming from? Of course, the answer is yes. Okay, so that you guys know. I know a lot of you are saying yes, but somehow somebody else with more honesty. Hey, listen, it's not that you're not honest or not honest. It's not. I mean, obviously, I don't see a current flowing through a bar magnet. So you have to explain that to me. Is that what you're owed to, basically? Is that what you're saying, Gareth?
If I hook up an ammeter, I'm not gonna measure a current.
That's absolutely right. So I like that because, okay, I probably would agree with you guys. It's a current, but you have to show me where that current is coming from and where it is going. So that's basically the question to it. The answer that we need to do. So the answer is yes, there is a current, but somehow we have to explain that. Okay. So, but before we do that, let's start with the basics first. So we have a charge, and that charge is moving as I showed in here. And I want to find the magnetic field at some point in here. So that's basically what the experience has shown. So this is where the charge is. At some point, it's somewhere. Okay, of course, it's moving, so it's not permanent position in here. So this is at this instant that I'm going to be conducting this experiment. I want to find the magnetic field at this point. So this is a point. Now the velocity is as shown, and the vector that connects these 2 points is this vector. It's working, guys. Everybody else had a problem with the password or what?
No, it worked.
Okay, for some reason they are having problem. Tell them I sent an email to Aaron with the correct link. So probably they are using the wrong link. Did they text you or what?
Yeah, he texted me.
Yeah, tell him that I sent him an email with the correct link and the password has been tested to work. I don't know what else I can do at this point.
Okay, all right.
Okay, thank you. So let's continue this one in here. I'm sorry for those of you who came late. Basically, there was an issue with another class, and that's why we had to take this drastic measures to make sure that our sessions are secure, basically. Anyway, so this is the idea. The plane formed by these 2 vectors, the vector V. This is the vector that connects where the charge is. So this is the position of the charge at this instant. And this is the point where I'm interested to go and put a compass in there and see which way the needle will point. The angle between these 2 is phi. I'm going to call it phi in here, these 2 vectors. The plane that these 2 vectors form is the plane between these 2. It turns out the magnitude of this magnetic field depends first of all on the medium. And the medium is expressed in terms of this constant, which is called the permeability of the medium. Okay. And there is a 4 pi, and the 4 pi is needed because of the geometry actually that you need it in there, times the charge times V times sine of phi and divided by this distance squared. I'm going to call it R. So this distance squared. And the vector follows the right-hand rule, basically. That's what this experience has shown. So again, this is an experimental law, basically, that you're going to be looking at and measuring it in the lab. So the direction of B itself follows the right-hand rule. So B as direction, because it's a vector, you need the direction, is given by the right-hand rule. Okay. Again, where V is the first vector, R is the second vector, and B will turn out to be in the direction perpendicular to all of them. There's so many cross products by this time. I mean, we just did two chapters on, or at least we're about to do the second chapter for this magnetism, but it's always there. I mean, you have to be very it's kind of very involved with the cross product. So this was the vector V. This is the R hat, namely the direction that I am trying to find the magnetic field in. So this is a vector R, this is a vector R hat. Okay, And the outcome, of course, is a magnetic field produced in that point in there. And that is where B is. Provided Q is positive. This is if Q is positive. If Q is negative, because everything is Q in here, so this right-hand rule will be flipped, okay? So again, for Q positive. If Q is negative, then again, you're going to have whatever comes out from the right-hand rule is not going to basically flip by 180 degrees. Note in here that if the velocity, in other words, if V and the point in which I'm trying to find the magnetic field are parallel or anti-parallel, there is no B there. In other words, if I'm looking with the needle here will give me some reading, or at least measurement device for the magnetic field. If I'm trying to find the magnetic field in this point or anywhere behind the charge, I will find no magnetic field. This is unlike the electric field coming from a charge. The electric field coming from charge goes everywhere in space. Okay. This one seems to only be of interest to where the parallel direction is, and that's why we use the right-hand rule. Actually, this one is more useful for it. So the way you find the magnetic field for a charge moving, this is the direction of where the charge is going to. So this is the direction of the charge. So the charge is moving this way, provided this is a positive charge. Take the four fingers from your palm basically and curl it. Whichever way it curls, that's actually how the magnetic field is produced by. This charge is moving. Okay, so it's curling that way, provided Q is positive. If Q is negative, take that direction and put it 180 degrees. So from a standpoint looking into the charge, this is a positive charge coming toward you. So this is a single charge still coming towards you. So if the charge is coming here out of the screen, this is how basically the magnetic field would look like. So it's creating a magnetic field that curls around it. There is nothing in front, nothing in the back, but the entire magnetic field follows the right-hand rule. Namely, this is the right-hand rule now. That would be the right hand, where the thumb is going to be the direction of motion of the charge, and how your hand curls is how the magnetic field is going to curl too. The magnetic field is a curling vector. It's a vector that goes around basically in a circle. Okay. So if the point that we're interested in happen to be this point, then in this case, and this is a 90-degree angle with respect to the tangent, then in this case, sine phi is equal to 1, and it's QV divided by R squared. So that's as simple as that. Okay. Any other direction that we're interested in will make a different, will involve that sine phi, I'm sorry, sine of the angle between the two vectors. So this is for a single charge. But how about if I have a wire that is made up of a huge number of charges? So what I do in this case is I take my wire. So this is, I'm going to draw a wire in here. Okay. So this is a wire that has a steady current of charges moving in it, and that's what we call the current. So basically, a current in this case is the current I, and it's flowing through this entire wire, and that means that there are charges moving at a certain rate. And remember from the discussion we had in chapter 26, this current depends on the number of charges per unit volume. And time is, of course, Q, time is VD, time is, of course, the cross-section in this case, okay? So that's the rate of charges, how many charges are moving per unit time, basically, okay? So that is what the current is, if you guys remember. So that's from chapter 26. Again, N is their number per unit volume, and Q is each one of them is carrying charge Q. V time is the cross section, or at least delta X time is the cross section. That is going to be the volume that I'm considering in here, divided by delta T. That is the rate at which the current is flowing. So if I take a single element of this wire, this is of a length DL, I'm sorry, let me write it delta L. It's much easier to work with finite quantities than to work with infinitesimally small quantities. But I'm going to assume that it's all in the same direction. And let's say, for example, I want to come to a point P in space, where I want to find the magnetic field. The fact I'm writing an X in here doesn't mean that the magnetic field necessarily is penetrating the surface or coming out of it or anything in here. Basically, this is a vector. This is a point in here. And I'm interested in finding what B is going to look like in that point in space. Again, these charges are drifting with the drift velocity VD in this direction, basically. And this is the point in space that I'm trying to find it. So there is an angle in here, phi. And each one of them is going to create a smaller and smaller magnetic field. And the combination of all of them will give me the total magnetic field. Can anybody tell me what in the world justifies the fact that if I have a contribution from one charge and another charge and another charge giving me a smaller and smaller quantity of magnetic field, when I combine all of them, that is what I'm calling the magnetic field. Who gave me that right? What kind of law or something that gives me the right to do that? Remember it? Okay, that's a charlatan answer. Our best friend forever, which is the superposition principle. Very good. That's really, I mean, there is actually honestly the same argument that we made there in class for the electric field still holds true. Namely that, okay, the fact that one charge creates a magnetic field by moving in one direction, another charge moving in the same direction, it doesn't matter which direction it is, we're saying in here, ignore the first charge and now focus on the second charge, find the magnetic field that it produces and sum the two, and that is the magnetic field or combined of the two of them. There is no reason why a single charge by itself in the presence of a second one will create the magnetic field in the second point as if the other one doesn't exist. The presence of two of them will impact the two of them, either one, and then the argument should draw. There is no reason for it will hold, but yet experimentally that's true. So we're going to ignore the point that argument in here because it works, and we're going to use the superposition principle by stating the following: that if I have a bunch of charges now, they are all drifting, and I'm taking an element dl. So actually what I have in here, I have this many charges, and q times, again, they are all drifting with the velocity vd, times l, the length in here I'm taking just l. So this is how many charges I have in this cross section. So this is how many charges I have, and they're all moving with the velocity vd in this case. And all I have to do, delta l, I'm sorry. And all I have to do now is use that same formula, except now I have to, if we want to use a cross product, times r hat now, where r hat is this direction, and divided by the distance squared, okay? And times, of course, each one of them has that factor which I'm taking out from u naught, divided by 4 pi, okay? And there is a question in here, basically. So in this case, this is a current I, actually. This is itself a current I. And there is a question in here, and that is actually a very valid question, and that is actually a very important note in here. When we were doing the electrostatic electric field, basically, everywhere we saw that one, we had epsilon naught. We were dealing with the permittivity of the medium. And the permittivity of the medium, we were always dividing by 1 over 4 pi epsilon naught. There was only one situation when we were doing the energy density for the electric field that turns out epsilon naught will be in the numerator. Everywhere else we were dealing with electrostatic electric fields, we were dealing with epsilon naught being in the denominator, and that's what represents basically the properties of the medium there. In this case, the properties of the medium, and I'm taking this whole observations in the air or in vacuum, are represented by mu naught. And mu naught now is not dividing by 1 over 4 pi epsilon naught, 1 over 4 pi mu naught, we're actually multiplying by mu naught over 4 pi. Okay? So whereas in the case of the electric field, epsilon naught lives downstairs, in this case, mu naught lives in the numerator, not in the denominator. I want you to make that note because it's critical later on trying to do equations and work the math and all of that, and we will have to make that distinction. Just by a vote right now, everywhere else from this point on, mu naught will be in the numerator. Just as much as everywhere else in the case of the electric field, epsilon naught was in the denominator. The only exception there was in the case of the electric energy density of the electric field, where epsilon naught jumps to the numerator. What do you guys think when we're going to calculate the energy density for the magnetic field at some point down the road, whereas mu naught lives in the numerator everywhere else? What do you think, what do you guys guess mu naught will be? Is it going to be in the numerator or is it going to be jumping down into the denominator? This is a guess. I need some feedback in here. Either on the chat. Okay, some people are still holding it in the numerator, and at least Sophia is thinking that it's going to jump down. And I think just before we continue this thing in here, it should have that behavior, or at least expect to behave the way Sophia is predicting. And let me tell you why. Because this is the properties of the medium. In the case of the electric field, it was in the denominator. And for some reason, when we're doing the energy density, it was 1/2 of epsilon naught times E squared. We're going to expect somehow, this is an expectation. There is no proof for it yet, but we will see it. That when we deal with the magnetic field, it's going to be somehow 1/2 again, but instead of mu naught upstairs, mu naught times B squared. Remember, in the case of the electric field, it was 1/2 epsilon naught times B squared. Okay, so I want you to watch for this expression once we arrive to it and see whether or not this makes sense, because this is the properties of the medium. In there, everywhere else in the electric field, we had epsilon naught downstairs, and when we dealt with this expression only, namely the energy density, it went upstairs, it went to the numerator. Whereas in this case, everywhere else, and this is what I'm telling you right now, we're going to be dealing with the magnetic field, mu naught will be in the numerator. So Sophia at least is thinking, and maybe she's right, maybe she's not, that mu naught should jump downstairs. Dimensionally, of course, it will make sense only if it jumps downstairs. We'll talk about that, okay? But we need to watch for this. We need to see if this makes sense. You guys see that? You guys understand that? Again, I really want you guys to, what I want you to take from these classes that I'm teaching you is, you need to start thinking ahead, and the more you think about these things, the more either it makes sense to you or not. That's one of the critical things I always ask for when you're solving the problem. Does it make sense? Of course, dimensionally it should make sense to you, and also in terms of properties of the medium, and try to come up with justifications. Now, if it doesn't make sense, we have to really think hard into why either our common sense is probably not correct, and we have to challenge that, or maybe we did something wrong, okay? One of the two things could have happened. So that's basically the law in here that we're going to be working with. So the magnetic field of a segment of a wire, so here's a segment of wire. This is not the whole wire, okay? This is just a part of it, of length dl, is going to be given by the magnetic field in any given point in space. Now it's a vector, mu naught over 4 pi times, there is no times in here. I was almost going to put epsilon naught in here. I, the current that is running through this wire, times dl crossed with this r hat, because at some point we're finding the magnetic field at some point in here. This is r hat divided by r squared. So this is the equivalence of your electric field, if you wish, for a point charge. If you guys remember, let me just put the analogy in here, and I want to put the analogy all the time in here. The electric field for a point charge was equal to 1 over 4 pi epsilon naught times what is it, Q times r hat divided by r squared. You guys see the difference between these two expressions and the analogies, other than mu naught and epsilon naught, which I just outlined right now? This is a time probably where you can turn on your microphone and start talking, because it may take some time in here to express anything. What are the similarities other than mu naught and epsilon naught? How are they similar?
You have the r hat and the r squared.
The r squared are similar, and that is important, actually. It's probably one of the most important properties of these two expressions, whether for the electric field or the electric field for point charge. This is not electric field or any other distribution, so that you are clear. And I can't have a monopole, if you wish. What I have in this case, I have a current, so I took a wire, a very long wire, and I've just focused on an element of which, trying to consider some sort of a point charge, okay? Point something. So in this case, what we're saying in here is that the electric field and the magnetic field, they both drop like 1 over r squared. And this is important analogy. This is a big deal. This r squared in the denominator. That's good, okay? Of course, the 4 pi, forget it, has to do with geometry of space. Anything else that you can see, r hat, the way it entered in the second expression, is it similar to the way it entered in the first one?
Well, in the for the magnetic field, you use the cross product, but the other one you don't.
Okay, that is actually the biggest difference between the two. Okay, one of them is straight out, basically just multiply. Q is just a scalar in here. Q is just the charge. Same thing with the current I. It's just a number current, which is just a number like 12 amperes or something like that. Doesn't matter. I mean, I'm talking in terms of math. I'm not talking in terms of physics now. I'm sorry, complications associated with this expression. The first one involves the cross product, and that is a nasty thing to be worked with. It's actually something that is probably not as yielding, if you wish, as the charge, which is just multiplied by the other one. I'm trying to grab my book in here, trying to see if there's some interesting applications or examples in here. And I hope that you guys have access to the book too. Okay, so it has here example 28.2, which is a good practice to work on this one. This is complicated. In other words, this expression requires some work in here. The word I use for this one, actually, there is a very scientific word that I think I use for this expression to compare to this one, and this is this word. Okay, this is not good. This expression is nasty. Okay. Oh man, I don't see you guys. I can't even see your reactions. They should, whether or not you're following me or not. Okay. You know what? This expression requires some honest work. I mean, it's really very, very complicated. So in the example in here, what they have in here, they have a wire, a long wire. So this is if you're following from your book. So they have a wire with a current. So for those who want to follow, it's example 28.8, 28.2, I'm sorry. So they have a wire with a current of 125 amps running through it. And the wire is, they want to take just 1 centimeter segment of it, okay? Small section of the wire. So you're not taking the whole wire, just taking 1 centimeter. And they want to find the magnetic field at a distance of 1.2 meters away from it. So let me redraw the wire because I drew it too close to the writing. So this is the wire again. This is 1 centimeter. And this is 1.2 meters away from it. So in this case, I want to find the magnetic field produced at that point. The current happened to be running in the negative direction. So if this was the positive x-axis, So the current I is actually moving in the other direction. So this is how basically I'm thinking about it. So the current is following this one. So if I'm looking at the top, it should be going in. You guys see that? So if this was the y-axis, and this would be the one that is penetrating the surface is the z-axis. So this one is in the negative direction in that point. You guys see that? Because it's going in and it's coming out. Had they asked us to find it in the below the wire, it should be positive. Do you guys see that? Had they asked us to find it here, 1.2 meters away in the bottom, it should be coming from the other side. So at this point, the magnetic field should be positive, and here it should be negative in the z direction. You guys agree on this? So let's put some numbers in here and see how we can find. The assumption that we're making in here, because we're just interested in the portion 1 centimeter, how much magnetic field is created by just 1 centimeter. 1 centimeter compared to 1.2 meter is a very tiny number. One centimeter is a very small number compared to 1 meter. So we're going to use this expression to find the magnetic field and replace this number by 1 centimeter basically, and do the cross product to find the magnetic field. So the magnetic field in that point should be, according to this example, first of all, I have to find dl times I, or dl itself. dl is the 1 centimeter length, so it's the delta L, but it's in the negative direction, so it's going to be negative in the I hat direction, because I hat is in this direction. So it's in the negative. dl has a direction of the current. So if the current is flowing in the negative direction, that means dl actually is in the negative direction too. It follows where the current is flowing. So we have that. R hat now, this is R hat. R hat actually is the y hat, is the j hat. So this is the number that we're interested in. So that's actually the unit vector in the y direction, in this x-axis. So now we have everything. We have everything now. So all we have to do is try and find that magnetic field. So the magnetic field B as a vector, this is only for that element of 1 centimeter, not the whole wire, okay? So it's going to be mu naught divided by 4 pi times the current I times dl with a negative number times I hat, that is actually this vector crossed with the j hat divided by the distance squared, and the distance squared is that basically, I'm going to write it as L squared in here, this distance of 1.2 meters from here, from where the wire is to where the point in space is. If we do that, then note the following from your cross product rules. I hat, okay, why is it not writing for me? Okay, I hat crossed with j hat is equal to what? Anybody? Did you guys do a lot of cross products in physics 250 or not?
Not really.
Okay.
Yeah, I think we did like 1.
Okay. Okay. When it ever fails, go back to the definitions where things come from, okay? How you do things basically. So again, we're going to use this definition in here. So I had j hat, which is the cross product as a matrix basically calculation. The unit, the vector I hat is just the unit vector 1, whose coordinates are 1, 0, 0. And the vector j hat in this case is the vector in the y direction. So it's simply going to be I hat times 0 minus 0 squared minus 0. So it's going to be I hat times 0 squared minus 0 times 1, which is 0. Okay. Minus j hat times 1 times 0, which is 0, and 0 times 0, which is 0. Okay. That's easy to do, actually. Plus, so you alternate when you do the determinant in this case, the signs. Plus, once you reach k hat times 1 times 1, that's 1 minus 0. So actually, I hat crossed with j hat is k hat. Okay? That's easy enough. And as a general rule, from now on, so that to save us a little bit of headache, if I do a cyclic rotation of these vectors, I'm going to find the answer based on this one. So again, I hat crossed with j hat is k hat. It's very easy to find why. I hat is 1, j hat is 1 in magnitude, that is, and the sine of the angle between them is 1, sine of 90 degrees is 1, equal to the vector in the direction of k, and that is k times 1 times 1 times 1, so it's 1. So it's basically k hat. So that's one thing. Now, if I rotate everything and move them around, so basically instead of j, I move it here k, so it's going to be k hat crossed with j. I moves to the place of j, and j moves the place to the k. So this is the product of k hat crossed with j hat. That's another thing that we need at some point in calculations when we're doing cross product. Now, if I continue this rotation one more time, move k one space, move I one space, and move j to the place of k hat. So j hat crossed with k hat is equal to I hat. This is one of the properties of the cross product. You can do a cyclic rotation, and you're going to end up with the same thing. In other words, if I start with this one being, what is it, j hat crossed with k hat, I go back into the I hat. So that's something that I was talking about earlier about the rules. Some textbooks, they will tell you that this one crossed with that one is equal to that one, and that's exactly the same thing. In other words, they're talking about the last expression. They're all the same. The only trouble with this expression is the second one. Usually you don't write it this way. You start always with the x-axis first, and then you move on. In that case, you have to flip that order, and you say I hat crossed with k hat. Okay, this zoom thing is the one that is, I think, causing things. So I hat crossed with j hat, and so crossed with k hat. When you flip the order in here, instead of k hat crossed with j hat, is actually, that's another thing with the cross product. If you go this way, you're going to multiply by sine of this angle. If you go the other way, you're going to multiply by sine of negative that angle. So the sign flips in this case, and it's going to be minus j hat. So that's the only thing that you have to remember. I mean, in general rule, A cross B is not the same as B cross A, so this operation is not commutative. It's actually equal to minus B cross A. So that's some of the properties of the cross product. This discussion, usually we do it a little bit more extensive in physics 250 when we start dealing with rotations. But now, since we're using it extensively, and I told you this chapter deals a lot with the with this cross product, you really have to know these things. So in other words, if anything fails, if you don't remember anything, just remember the matrix thing, okay? And you're going to find the correct answer. So the bottom line is that cross product I hat cross j hat is nothing but k hat. And that's exactly what I was saying earlier in terms of the magnetic field. This is going to be in the negative direction in the k axis. So the B that is produced in that point should have, first of all, I have a minus sign, and that minus sign is coming actually from the x, from the current itself. So I have a minus sign in the expression, minus times mu naught divided by 4 pi times the current I times dl, delta L, which is 1 centimeter, divided by r squared, and r is 1.2 meters, k hat, exactly how I expected. Now it's just a matter of plugging in the numbers, basically put everything together. One thing you need to remember is that mu naught over, and this is something you will be given in any exam or something like that, is mu naught over 4 pi is 10 to the negative 7 in SI. So if the force is in Newton, if the distance is in meters, if the current is in an ampere, and the magnetic field is in Tesla, this is the value you're going to be using for mu naught, which is 4 pi times 10 to the negative 7. But it comes in bundled as a number, which is 10 to the negative 7, mu naught over 4 pi. Plug in all the numbers. They gave the current to be how much? 125 amps. And they gave you the distance r to be 1.2 meters. And they gave you delta L to be 0.01 meters. So I have all the numbers, and if I plug in the numbers, let me tell you how much the magnetic field turned out to be, at least according to the book. B will be negative 8.7 times 10 to the negative 8 Tesla in the k hat direction. So as we expected it, we expected the charge is moving this way, or at least the current is going this way. The magnetic field on top of the charge, on top of the wire, will be in the negative direction. If I continue, my hand is going to be coming out. So if I plug in everything with the same, it will be the same except for the following thing. The r hat now, this r hat will be actually not in the positive j direction, but it's going to be in the negative j direction. So this means that negative will make it positive. So if I'm doing it in the bottom of the wire, I'm going to find the same number, the same value as 1.2 meters as this one, and also it's going to be positive because j hat will be positive in the bottom. Do you guys see the difference in here and how we're getting with the signs correctly? One thing also to note in here while we're doing this, look at the value of the magnetic. It's extremely small. And if you want to find the electric, and then you have to find the electric field of a single charge and see how many charges are in that region in there, you find the much bigger electric field. Magnetic field is a much weaker value than the electric field, at least number-wise. Put them everything in SI units, basically. The magnetic field is in Newton per Coulomb, and the electric field in Newton per Coulomb, and the magnetic field in Tesla. And they want you again to find another point actually over here of interest, and it's a point that is actually still 1.2 meters. So this point is 2.2 meters. That is making a 30-degree angle. Okay. Now the algebra is a little bit different. Okay. So this is a vector that we need to somehow find. Okay. So we need to find the unit vector r hat. Okay. And once we find the unit vector r hat, everything should be the same. So let me draw this portion here for that point in there. I know the book did this a little bit differently, but I want you guys to have the feel of how these problems work, because you're going to be doing problems for this for this class. I mean, a lot. So you have a wire still with the current running in the negative direction. So the current is still in the negative I hat direction, and I'm trying to find this point in here because at some point I'm interested in doing basically delta L, which is in the negative I hat direction, okay? And I'm going to cross it with this unit vector r hat, okay? This distance is 1.2 meters, I know that. And this angle, they tell me, is 30 degrees, okay? So how am I going to do that? First of all, you can clearly see, guys, that the r vector itself, not r hat, has a negative component in terms of the x-axis and a positive component in terms of the y-axis. Has this component in the y-axis parallel to I hat, and have this component which is anti-parallel to I hat. This is j hat, I'm sorry. Parallel to I hat in the y-axis and anti-parallel to the I hat direction in the x-axis. Yes? Good? Okay. Aaron just joined in now, so apparently he's we're doing example from the book, Aaron. I don't know if Julian is here or not. Let me quickly check here. For some reason, Julian also did not join us. Probably still have some difficulty with the link. Okay. We're doing example 28.2 from chapter 28. Okay, Aaron. Let's start with chapter 28. So we're trying to find now that r hat vector. Here is, at least in terms of practical problems, and we'll have a lot of them in this chapter, so we really have to remember this technique. R hat is r vector divided by r. Okay? Simple as that. Take any vector divided by its magnitude, you're going to find the unit vector in that direction. That's basically as that. So I know the length of the vector is 1.2 meters. So I'm going to write it in that fashion. That way I know basically how to express this vector. So in this right angle triangle, this angle of course is 60 degrees. Hey, Julian, you're with John. That's good. Okay. Okay. So so that's basically You guys, at least Aaron, I sent you the correct link. Can you tell me if the new link is working for you or not, or what was the problem earlier? You can tell me in the chat, or you can tell me with the phone. I mean, with the microphone. Because I'm worried about that thing.
It kept giving me like invalid password like all the time, and I was entering the same thing over and over, and then suddenly it just went through.
Oh, I think probably the link was something probably problematic or something like that. But I know I tested it after we were in here and it worked. Anyway, hopefully you can bookmark that link and you can save the password, then we don't have to go through this thing again.
It's the same password all the time?
Yeah, the password is not going to change. So once we have that one, you can bookmark it actually, and it should be working.
Okay.
Okay. So basically, that's the technique to finding this thing in here quickly without having to go a lot, because we have some other things to do. I know we still have about 20 minutes to finish this thing. Basically, in here there are two components. There is component along the I hat direction, and there is a component along the j hat direction for this r hat vector. Okay, and the thing to remember is you're going to cross it with I hat because you're going to multiply it by delta L at some point. You're going to do delta L with the unit vector. Here is the expression. Delta L crossed with R will have two components in it. So at some point, you will be dealing with I hat cross with that. That is 0. Cross with itself is 0. And why is that? Very easy to see why. It's A, the length of A, times the length of A, times the sine of the angle that is sustained between the vector and itself. And how much a vector does between itself? It's going to be 0 degrees, isn't it? That's basically what that means. So this angle is going to be 0. So this value is going to be sine of 0, which is 0. So any vector crossed by with itself is 0. So, and that is important because the vector r hat has two components, one along I hat direction and one along the j hat direction. The one along the I hat direction will be basically 0. Okay. And because the delta L is along the I hat direction and r hat has two components. So at some point I'm going to do that and it's going to give me 0. So we'll be left just with I hat, the j hat crossed with the I hat, and that is going to be a given value. That is not going to be 0. Actually, it's going to be k hat. And but that component of r hat is just this value, which is just cosine of this angle 30 degrees. That's the opposite to 30 degrees. So it's this value without having to do a lot of calculations multiplied by cosine of, what is it? I'm sorry. It's the cosine of this whole angle, which is going to be a, wait a minute, the 30 degrees, where did I put the 30 degrees in here? Did I put it correctly or not? Cosine of 100 cos minus 10. Actually, it's going to be a, okay, we really have to get that vector r hat correctly, okay? R hat is a minus, yes. It's the opposite to 30 degrees, not the adjacent to 30. Why did I say it's the opposite is not cosine, it's a sine, okay? You guys need to correct me. It's clearly the opposite to 30 degrees, no? So it's the sine of 30 degrees. So it's going to be the same answer times that component. And that component involves the opposite to 30 degrees, and that is going to be actually sine of 30 degrees. So whatever sine of 30 degrees multiplied by this number is going to be the correct answer for that magnetic field. The point I'm trying to say in here, and I get too much focus on this idea of product, sometimes forget about the projection of vectors, that look, when you're dealing with r hat crossed with any other vector, pay attention to the components. If the vector is going to be at some point I hat crossed with I hat, it's easy about that. Any vector is going to be 0. Since I'm dealing with components of r hat along the x-axis, that I can ignore. Forget it. Just focus only the components along the j hat direction. And the components along the j hat direction is the opposite to 30 degrees, and that is sine of 30 degrees. So whatever value you found earlier, multiply by sine of 30 degrees, and that's it. Okay. If you want to, you can go in detail about this problem in your book. Okay, in the example in the book. So I wanted you guys to have a feel also of the cross product because that's important for the entire chapter. So you really have to have that. Any questions so far? Okay. No?
Are you saying it was 28.2, but mine is a different question on that.
Yeah, 28.2, yes, that's the example in there.
On 15 or 14 edition?
I'm looking at the 15th edition. That's the one that's the one I look at because that's the one the publisher sent me. And okay. Is this different?
No,
Yeah,
I was looking at the 14 one.
If it's different, take this one as an example. I'm just putting as an example, and the biggest focus of this example is not the. Okay, that's really not good. Let me stop sharing this. The biggest thing in here, let me take quick attendance in here. We're missing quite a few people today. We're missing Jackson because he had a problem with the internet, he told me. That's one person. And who else? Julian is actually sitting with John. That's good. So we're missing. Andrew is not here. And that's two people. Sophia is here. Okay, so let me take a snapshot quickly here of what we have. Okay. So let me continue this one. So we have 9. We're missing 3 people actually. Who else? Gareth was here. Oh, Gareth is here. Sorry. Somebody else. I don't know which one is it right now. No, actually 2 people only because no, actually it's actually 3 people, 4 people. We'll find them. We'll find who they are. John and somebody else. Okay, we'll find them. Anyway, so let me continue with this discussion here because the next part of the chapter is actually very, very important. That is actually going to be the essence of everything. Put it this way. So let me continue. That is probably the most complicated portion of this chapter. That is trying to electric field. I mean the magnetic field due to a wire of length . So again, so I have a wire in here, and it's usually by symmetry we take its length to be 2a. Okay, so we're interested in somewhere in here in the center in the axis of symmetry of that wire, and we're trying to find the magnetic field produced by this wire. So this wire is, of course, is a long wire. Of course, this is not practical. Okay, how can you have a current running through a wire like this? It has to be connected somehow. But the wire is so long that this is basically the focus that we have in here. And we're going to go distance y from the wire in the center and trying to find the magnetic field as this wire produces. Do you guys understand the setup of the problem? Yes? What happened to my chat session? Did it go away? It went. So I need the verbal confirmations because sometimes they lose that, especially when I switch screens. You guys understand the setup?
Yeah.
Okay, very good. So here is the problem. We want to find B in that point, okay? Here. How much is B? That's basically the question. So what I do in this case, what we just like what we did in the case of the electric field, is that we take a portion of this wire. This is the x-axis again. This is the length of the wire, but the x-axis extends beyond that. So we're going to move a distance x from the origin and take an element of length dx and consider the current running through it, and it's going this way. It's going in the this side, as far as I'm concerned. I don't know which side you have it in there. When you're looking at the screen, probably it's going to be looking different. But the point being is, you have to follow it with your hand. So I'm going to go up and find the magnetic field. The magnetic field up, this is the x-axis. This is I hat. This is j hat. So by the right-hand rule, actually the magnetic field will be in the k hat direction, okay, overall. So that's basically what we're trying to find. A vector that is going to be in the z direction in this case, perpendicular to both the wire itself and perpendicular to actually the vector connecting the point, the wire, and the place where we want to find the electric field, the magnetic field. The point in here is that the formula does not give you in terms of y, it gives you in terms of this distance. And that is the formula, that how it works. This is r. How much r is in terms of x and y? Let me draw the geometry again clearly. So this is the center. This distance is x. Taking an element of length x plus delta x. And this distance is y. Trying to find the magnetic field in that point. So how much is r from this geometry?
Square root of y squared plus x squared.
You guys agree with him?
Nah, I'm talking nonsense.
Okay. Tim, do you confirm? Tim or Gareth? I can't see the chat. If you guys are chatting now, for some reason it's gone, and then I'm not.
I'm gonna claim nonsense. That looks good.
Okay, very good. So that's the distance. That's very basically a Pythagorean theorem. We're trying to find the magnetic field in that point. Here is where r hat is. It's a unit vector connecting the place where we're trying to find, from where we're trying to find the magnetic field up to the point where we're finding it. So that's r hat actually. And this is I hat. This is j hat. And k hat is perpendicular to both of them and coming out of the surface. And the integral is still from minus a to pi plus a. So we're going to use a superposition at some point and say this is the total magnetic field. Take every single element of length dx and add it up from negative a to positive a. So that's basically the bottom line. So we need to find, first of all, the magnetic field produced by this part of the wire, which is of length delta x. So that part of the wire will give me magnetic field delta b, which is simply equal to mu naught over 4 pi times the current that is running through wire times the length is delta x, and the current is moving in the positive direction. So it's still delta x times I hat now. It's not like the previous situation, which was moving in the negative direction. Now cross with r hat divided by r hat squared, and I mean divided by r squared. And r squared, we know it's y squared plus x squared. So everything seems to be in great shape. Okay. Instead of dealing with these things, I'm going to introduce this angle theta. Okay, obviously the angle theta, I need to deal with it correctly. Okay, and the angle theta from the geometry, the tangent of this angle theta is clearly equal to x over y, opposite over adjacent. Okay, I'm going to introduce that angle theta, and since I'm dealing with the angle theta, now I'm thinking this vector r. This is the vector r itself, not r hat. And divided by r is going to be my r hat. Again, this is what I told you earlier. And this vector, if you guys clearly see, it's the sum of these two vectors. This vector plus that vector gives me r. Yes?
Yeah.
Now, this vector in here, it's not x times I hat, but it's minus x times I hat. X times I hat is a positive number. This one is x times minus times I hat, but it has to be in the negative direction. So let me write the vector r since I just found it. The vector r is the sum of these two vectors. Minus x times I hat plus y times j hat. That's clearly from the geometry. You can clearly see this vector r is the sum of these two vectors going from the starting point where the vector r started in the opposite direction of the x-axis. So it's going to be in the negative direction by an amount of x, and then going up by an amount of y. So that is basically what that vector looks like. Now, all I have to do is just worry about this r hat, because the expression doesn't involve r, but involves r hat. And r hat, as I just said before, it's simply r over, the vector r over r itself, the length r. So that's when you take a vector of its length divided by its length, it's going to be the unit vector in that direction. Okay. So having said that, now we're ready to do things. We're ready to look at this expression this way. So this is minus x over r times r hat, times I hat, sorry, plus y divided by r times j hat. Now x times divided by r, x divided by r, that is actually the sine of the angle theta. And y divided by r, that is the cosine of theta from that angle that I just introduced. From the geometry, this then the r hat itself is minus sine of theta I hat plus cosine of theta j hat. So that's what that unit vector r hat, what is it in the expression? That's what the r hat look like. I crossed with I hat, and that's exactly the big thing I was talking about to you guys about. I'm going to multiply this whole thing by I hat, so I'm going to focus on this part first. I hat crossed with r hat. What is that going to look like? It's going to give me I hat crossed with something that has I hat in it, and that is 0, plus something that has j hat in it, and that is, according to my earlier argument, is k hat. So I hat crossed with j hat is going to be I hat. So the first part is going to be 0. So it's going to be I hat crossed with I hat, and that is 0 because the sine of 0 is 0. So the last part that this whole thing boils down to is a positive first, because cosine is times 1, of I hat crossed with j hat, and that is k hat. So I'm done with this part. Okay, that's a big deal. Cross product. We know the vector is going to be in the z direction as we thought it should be, and that it is correct. So it's going to be in the k hat direction. So it's not the issue of the direction. Now we have to find the rest of the stuff and sum through everything. So let's go back in here and write what we are in right now. So the magnetic, this is just from that element of the wire, not the entire wire, by the way. The wire extends from minus a to positive a. Is mu naught divided by 4 pi times I times delta x times cosine theta divided by x squared plus y squared, and this is k hat direction. Okay. At this point, basically, if you follow the textbook, it tells you to sub the value of cosine theta. Remember, cosine theta r over r, so it's going to be x over r, and you're going to do that calculation and go around it, and it's an integral that requires a little bit of work. I don't like to do that. I like to do the other way around. Look at the expression x squared plus y squared, which is r squared in this case. But if I go back into my substitutions, x over y is just tangent of theta. So I'm going to pull the y squared from the denominator and use that fact for me. That fact for me. So I'm going to take advantage of the fact that tangent theta is just x over y. Y is fixed. Y is the distance we're trying to find the magnetic field from. So y is not changing. X is the one that is moving from negative a to positive a. So x is the problem that we have to deal with. That's why we have a delta x in the expression. So in this expression, first of all, we're going to sub it in here. So I'm going to pull the x from this, the y from this expression, and it will be left with 1 squared, which is 1, plus x squared over y squared, and that is tangent squared of theta. But I will have a y squared coming out. So the magnetic field as a vector is going to be equal to mu naught over 4 pi times y squared. I pulled the y squared already. I have delta x in the numerator times cosine of pi, cosine of theta, I'm sorry, times k hat, divided by, I'm left with 1 plus x squared over y squared, which is just tangent squared of theta. Okay? It seems like everything is telling me to use theta instead of x and y and all of that, because as x changes, so does theta change. Okay? So this integration can be changed from this one using the fact that d theta over cosine squared of theta, or d theta times secant squared of theta, is exactly dx over y. Y doesn't change, y is constant. So delta x then becomes, from the above expression, delta x is nothing but y times delta theta over cosine squared of theta. And now, having made that last substitution, everything now will be in terms of cosine theta and nothing else. So I know we still have about 4 minutes when we need to finish this one, but I want to get the point across quickly. So delta b then is going to be equal to mu naught over 4 pi times y squared. Remember, I just pulled the y in here from the delta x in that expression in the numerator. So I have a y times delta y theta over cosine squared of theta times 1 over 1 plus tangent squared. Actually, is a cosine squared of theta. That's actually another identity in here. In other words, that's 1 over secant squared. So cosine squared of theta. So when you take it to the numerator, it's going to be cosine squared of theta. And don't forget, I have already a cosine theta somewhere. So I have a cosine of theta in here. The cos squared cancels the cos squared. The y squared cancels one of the y's. And I will be left with the magnetic field now as a vector times k hat, of course. Don't forget your k hat. This is the vector set. So times delta b is just mu naught over 4 pi times y, because one of the y's cancels. Cosine squared cancels the cosine squared, but I'm left with the cosine theta times k hat and times delta theta. All I have to do now is integrate this expression with respect to theta and find the magnetic field. With integrate theta, the integration boundaries change not from from negative a to positive a, but from this angle. This is negative a. This angle, whose I'm going to call theta naught, whose tangent is equal to a over y, and that's it. Basically, that's the whole point of it now. So let's do that. So the integral of a cosine is going to be a sine, and the magnetic field in that point in here, B, is going to be the integral of a cosine as a sine. Of course, I took the limit when delta theta goes to d theta, and dB, the delta d becomes dB, and then sum it using the superposition principle. And so the value is going to be 4 pi y times sine of theta, evaluated between that angle, theta naught, which is I'm going to find, times k hat. So that's the integral. I already did the integral for you guys, and the integral of cosine is easy enough that it's sine. So, and the sine of theta sine of theta naught, I'm sorry, sine of theta naught is actually twice sine of theta naught. So the 2 cancels the 4, and I'm left with the expression that b is equal to mu naught over 2 pi y times sine of theta naught in k hat. Okay. And sine of theta naught from this geometry is the opposite, which is a, divided by square root of a squared plus y squared. So that's exactly how the result is actually presented in general in all the textbooks, you know, not just ours. Doesn't matter what version we have, it's the same result. So the magnetic field is going to be expressed now as the mu naught over 2 pi y. Y is the distance from the wire at the center, times sine of theta naught is a over the square root of a squared plus y squared and times k hat. Now, in the limit, we'll have about a minute and a half to finish this. In the limit, when let me first of all do another thing in here. I'm going to pull from this expression a squared before we do the limit, okay? So it's going to be b times mu naught over 2 pi y. In pulling a, so I'll have an a in here, and I will have an a in the denominator. So I'm left with a 1 times y squared over a squared times k hat. The a cancels the a. Now I can think about this problem and say, okay, if I have a very, very long wire compared to the distance y. In other words, if y over a is very, very small compared to 1, then this one can be said to be 0, And the result for the magnetic field, again, is going to be for a very long wire, is going to be simply that square root is gone and the a is gone. So the expression will not depend on a and the square root, so as expected. We're taking the limit when a goes to infinity. So this is a very long wire. If you're interested in trying to find the magnetic field for it times I. And this is k hat. Okay, did I forget? Yeah, I think I did forget the I somewhere. Please correct your algebra in here. There is an I missing. Without the current, of course, there is no somehow it dropped it when we started doing the without current there is no magnetism. So current is the one that causes magnetism. And I think we started in here. Okay, I can hear this. So that's basically the magnetic field produced by a wire of length I mean of an infinite length. And this is the magnetic field at a distance y from it. I'm going to make this notes available for you guys. I'd like you to go through this derivation again, trying to have an understanding of these things. I know the book gives you the version of, and that's really long. I think the polar coordinates are a lot easier. And when you, even with the electric field, that's easier to do with that one than this one. Any questions before we call it today? Because I think what I'm going to do is, before you ask a question, I'm going to continue this lecture, recording it, and then I'm going to post it on Canvas, and we'll continue the discussion on Tuesday when we meet. We're going to meet at 8 o'clock again, and we're going to do some problems from this chapter, and also you will have an assignment for homework for this chapter, and hopefully we start next chapter 29 by next week, and so that we'll be ready for our lab by a week from Tuesday of next week. And if you have any questions, please, you can ask them now, or you can ask them on Canvas. No? No?
No.
No.
Okay, I'll see you guys in a week from last Tuesday. Tuesday, basically.
When are you going to post the homework?
The homework for this chapter should be posted this way or this weekend, because we did a great deal on it. Okay?
5 questions, right?
Okay.
5 questions, right?
You have a question? Go ahead.
No. You're going to put 5 questions or 10 questions?
Oh, for the homework? No, we need to be doing stuff. Okay, now we're sitting at home doing nothing. At least we have something useful to do. Okay. Okay, see you guys.
See ya.
Okay, bye.
All right.
Okay, bye.
All right.